Hello guys and welcome back to another class of our course about the complete introduction to quantum computing. So in today's class our main topic would be about mathematics and we are going to talk about numbers in general. So basically a really important concept in quantum computing as well as in quantum mechanics are complex numbers, and basically you will need this concept to be able to understand a little bit more. Well, in my opinion, you need this concept to understand a little bit more the concept of quantum computing and to understand quantum computing as a whole. So what we are going to do today is really having a basic introduction to complex numbers, so you guys will be able to understand what exactly this is, how it works, and basically how you can represent this on a graph. So let's start. Alright, so basically the first thing that we need to understand is what is a number exactly. So yes, the majority of you will say a number is 1, 2, 3, 4, 5. Yes, this is true. But if we take the definition, basically a number will be a mathematical object that is used to count, measure, and label. So as you guys thought, it could be represented as 1, 2, 3, 4, 5. Once again, those are natural numbers. But there is more than just natural numbers. We have natural numbers, we can have negative numbers that will be, for example, -1, -2, -3, -4. We have rational numbers that will be all fractional and that can be possibly fractionable numbers. We have irrational numbers, so in this case, it will be numbers that can be fractionate. Because, for example, the square root of 2 or the square root of 5. So basically those numbers are irrational numbers. We can have infinities, which would be different type. Well, you have infinities and different type of infinities. You have transcendental numbers, which could be, for example, E, that is 2.72, etc., or P, which is a really popular transcendental number. Finally, we have another type of numbers, which is complex numbers, that will bring us to the point number 2. And basically, what exactly are complex numbers? So complex numbers, to understand them, are simply numbers that actually, well, that until now don't really exist. Well, those are not, we can't say imaginary numbers. Well, we call them imaginary numbers, but for the moment we can't prove their existence. So basically, let's say the square root of a would be equal to -1. So basically, it's not possible to have a square root of something that, a at 2 will be equal to -1. So basically, it's not possible to have a number that will be at power 2 and it give us 1, because the square root of, let's say, a certain number will be plus or minus another number. But if we put this number at the power of 2, it's not possible. So what's my mistake? So let's say, for example, you have a at the power of 2. So basically, if you put a at power of 2, even if it's a negative number, it will automatically become a positive number. Because, for example, let's say we have -2, a equals -2, and it's at power of 2, and basically it will be 4. So the answer will always be a positive number. But if instead we have, let's say, a at the power of 2, and it give us a negative number, basically we don't know what a is. So this would be a complex number because we can't really prove that it exists. What's the difference between all numbers and complex numbers? So as I explained, it's really hard to work with complex numbers because, once again, they don't really exist. We suppose them hypothetically, and you will see in the future graphs how we can represent them. Well, how we can represent them on a chart. Basically, other numbers, well, we can work with them. It will be, for example, 1, 2, 3, 4, 5. So you can work with rational, irrational numbers, negative, positive numbers. You can work with all types of numbers. And basically, with complex numbers, it's a bit more complicated, but it's possible. So an example of a number, for example, in this case, we can have 5, that is a rational number, -20, that will be a negative number. So we have P, E, that will be, in this case, transcendental numbers. You can have, I don't know, 3.75, that can be another type of number. And we have complex numbers. So as you can see here, we can have an example of complex numbers. So in this case, we can have I at the power of 2, that will become -5. So in this case, I, even if it's, I don't know, if you can choose the number that you want. If you take any number at the power of 2, it can't become a negative number. So basically this is impossible. And those will be simply other examples. So in this case, we have a function, and let's say, for example, 5 is a complex number, so basically it's going to become complex. So you will have one part of this function that will be not complex, so it will be a normal number, a rational and normal number that we can work with. So in this case it's going to be 3, in this case it's going to be -7, and the 5 right here will be part of the irrational, not irrational, of the complex number. So how exactly we can put this all on a graph? So it's possible to show those types of functions on a graph. And basically how exactly this would work, so let's work with this function right here, which is 3 plus 2g. So in this case, if g is a imaginary number or a complex number, so what we will do is pretty simple. We'll use the x-axis as real numbers. So basically we'll put our real numbers right here, and g, or well, here we'll put our y's. We'll use our y's as imaginary numbers. So pretty simple, we'll have our function right here, which will be 3 plus 2g. And we want to represent, well, we'll have this number right here, 3 plus 2g. It's not really a function. And we want to represent it on a chart. So pretty simple, what we'll do, we'll simply put the 3 right here. So basically we will have our real number, which is 3. And we'll simply select 3 right here. And 2, since it's a part of our complex number, we'll put it right here. So basically to represent our complex number on a graph, it's gonna be like this. So as you can see here, we'll have our complex number that is represented this way. But since we don't know what g is, we'll simply use the 2 to be able to represent it. So basically here we have our x's, here we have our y's. The x's will be real numbers and the y's will be our complex or imaginary numbers. So as you can see, I explained it right here. So for this number right there, the real number of this operation will be 3 and the imaginary number will be 2. So another type of representation. So basically here you have plenty of complex numbers that you guys can see. So this operation right here explains it really simply. So we'll have our a will be our, in this case, a real number, and b will become part of the imaginary number axis. So in this case, let's see a few examples. So for example, we have our 3, in this case it's going to be our a, and our 2i will be our b. So basically here our imaginary number will be right there. Same thing for if, for example, the number is negative. So it could work for both. So for example, if our a is negative, we will put our number right here. So a negative and b positive, it's possible. A and b negative, it's possible. Just b negative and a positive, it's possible as well. So as you can see, this is the way that you guys can represent a complex number on a graph. Once again, it's pretty hard working with those numbers, but it's possible. And this is a really important concept to understand, well, to understand for the future classes, and simply to understand for quantum computing. So as I explained today, we talked about numbers. Just to summarize everything, we talked about numbers, we talked about all types of numbers, as well as complex numbers, which is really important in this type of computing. So I hope you guys understood everything. So that's it for this class, guys, and see you all in our next class.